All right, so the problem of the day we're looking at looks at a reaction from first term. And in this reaction, we're swapping off a bromine and forming a sulfide. Do you guys think this is going to be SN1 or SN2? Raise your hand if you think SN1. Raise your hand if you think SN2. In this case, it's a little deceiving because if we think about what happens, if the bromine were to pop off on its own, we would form a carbocation on a secondary carbon. But what would be special about that carbocation? Resonance stabilized. So in this case, it would actually prefer to undergo an SN1 reaction because we would form a really stable benzylic carbocation. So in this case, the reagent that we need is thiomethane, which I was telling people earlier is one of the most horrendous smelling compounds you can ever work with. It's quite possibly the worst smell you've ever smelled in a bathroom times a million. So this wouldn't be an enjoyable reaction, but luckily we just get to look at it on paper. All right, so now let's look at the product. How many unique sets of protons are there? I'm going to go through and I'm going to actually draw in all of the protons on here, which I saw a lot of people doing. We've got 3 of them over here. Got 3 of them over here. And then last but not least, this little guy right there. All right, so we've got this aldehyde. Are there any other protons like that aldehyde? No, right? There's only one aldehyde group, so that proton is unique. What about this proton on the benzene ring? Whoop, that should be HB. Are there any protons like HB? I heard some people mumbling yes. The one on the bottom, right? If we think about that aldehyde group can spin around like a rotor because it's attached via a sigma bond. So that proton right below HB on the other side of the ring is actually equivalent. So both of these are their own unique set. So we'll call those both HBs. What about HC over here? Let me actually move HC a little bit more out of the way. Does that have any other protons like it? Yeah, same thing. On the other side of the ring, it's going to be in that equivalent chemical environment. All right, what about HD, this little guy right there? Are there any like it? No, it's pretty unique. What about these methyl group ones? I'll call these HE. We know that methyl groups are always going to be equivalent. Is the other methyl group equivalent to this methyl group? So if we look at this methyl group, it's attached to a carbon that's in between an aromatic ring and a sulfur. The other methyl group is just attached to a sulfur. So they're in different chemical environments. So these would be HF. All right, let's make a little list over here. And what I'll do is I'll label this proton. And then I'll label this integration. And then I'll... Whoa, shoot, sorry guys. I'll label this multiplicity or M, and then I'll label this as delta. And we'll make a little chart here. All right, so proton A. How many protons make up that set? 1. So we can immediately say proton A has an integration of 1. What should proton A be split as? How many 3-bond neighbors does proton A have? 0. So if it has 0 3-bond neighbors, what should it be split as? A singlet, right? So I'll just call this S for a singlet. And then if we look at the shifting pattern, you can grab out the sheet that I gave you guys with the correlation value. Where do aldehydes typically show up? Around where? 9 to 10. So we'll say 9 to 10 ppm. All right, now let's go to proton B. How many protons are in the B set? 2. What should proton B be split as? How many 3-bond neighbors are there to proton B?
1. So double it.
There's 1 3-bond neighbor, so it's going to be what? Double it. So I'll label this D. And where do aromatic protons show up? 6 to 9 ppm. So if you look at your correlation sheet, those aromatic protons should show up there. Same with proton C. It should integrate as 2. It should be a doublet, and it should be 6 to 9 ppm. What about proton D? What does it integrate as? How many protons are in its set? 1. So we can just label this as 1. How many 3-bond neighbors are there to proton D? There are 3, right? So if we look at HE, that proton, or those protons on that methyl group, those are 3 bonds away. There's 3 of them, so what should this split as? A quartet, so I'll label this Q for a quartet. And where would this one show up? This one's a little tricky for the chemical shift. If we look at it, it's on a carbon that's attached to an electronegative group. On the correlation sheet, an electronegative group is just drawn as an X. So 2 to 4, and it's also on a carbon that's attached to an aromatic ring. So 3 to 2. Those effects are cumulative. So this will probably show up closer to 4. So let's go ahead and just label this approximately 4 ppm. Because both of those effects, that polarity effect and that effect of being near the aromatic ring, kind of get added together a little bit. That means they're going to show up even potentially above 4. All right, let's do proton E. How many protons are in that set? 3, right? Pretty simple. How many 3-bond neighbors are there? There's 1 3-bond neighbor, right? Proton D. What will proton E get split as, or the set? A doublet, right? So we'll label this as D. Where do you think this one will show up as? Not everybody all at once. It'll show up in that CH region, which is where?
2 to like 1.5.
Okay, so we'll say 0.5 to 2 ppm. Somewhere in that range. All right, last but not least, proton F. What will it integrate as? It'll integrate as 3, right? We've got 3 protons. Are there any 3-bond neighbors? No, so what will its multiplicity be? Singlet. And then where will its chemical shift be? 4 to 2. Or 2 to 4, however you want to lay it out. All right, so now we've got all the data that we need in order to make our graph. So we'll go down and we'll look at our NMR spectrum, or our pretend NMR spectrum. Our aldehyde, we said, should show up between 9 and 10, and it should be a singlet. So I'll just go ahead and draw in a singlet there. We've got 2 doublets in that aromatic region. Somebody was asking me, do those overlap perfectly on one another? It's pretty rare to have peaks overlap perfectly, so they're going to be offset a little bit, kind of like you're holding up 2 number 2s. And if you do that, you'll probably have a peak that looks like this, and then another one that looks like that. So now we've got 2 doublets. All right, next one over, we should have a quartet around 4. So I'll go ahead and write in this little itty-bitty quartet. We know that the quartet should integrate as 1, so the area underneath the peak for that quartet should be about the same area as the peak for the aldehyde. Does that make sense? Yeah? Okay. And then the next peak, if we go up, should be around 2 to 4, and it should be a singlet. So I'll go ahead and put a singlet right around 3, and it should be pretty large because it integrates to 3. Oh, let me make that a little bit better. All right, so now we've got a peak that integrates at 3, and then we've got another doublet that we need to include between 0.5 and 2. So I'll put in a doublet. Right around there. Oftentimes what people will do to show the integration pattern or integration values is they'll put this little curvy arrow above here. Whoop. Let me try to fix this. And what this expresses is the area underneath the curve. That means this one's going to be a ratio of 1 to 2 to 2. And then if we go over here, what's the integration for this one? for the quartet? What's the area underneath the peak? 1. So we'll label this as 1. What about the area underneath the big singlet at 3? Should be 3. So oftentimes this curve will be about 3 times as big. And then same thing with this one. This will integrate as 3. So this is what the NMR spectrum should roughly look like for this molecule. So before we experimentally take or acquire an NMR spectrum, we can anticipate what we think it should look like and then compare our data to our prediction. And so what we're going to be doing today in class is kind of going through this same methodology. The first step is you want to identify the number of unique proton signals. Next step is identify the integration, so how many protons account for each signal. Step after that is you need to figure out how that signal is split. How many 3-bond neighbors are there, essentially? If you've got 1 3-bond neighbor, it'll be a doublet. 3 3-bond neighbors will be a quartet, and so on. And then the last part is to anticipate the chemical shift. This time what we're doing is we're going to kind of flip it, though. So if you open up the in-class activity with the problem set, I've given you the spectrum and the molecular formula, and I'm asking us to figure out the structure. So same kind of rules apply, we're just doing it in reverse and analyzing it the opposite way. There are some really useful tricks that I'll show you guys, so we'll work through this first one together. Before we do anything, let's determine the HDI for this molecule. So what do you guys think the HDI would be for this? It's going to be 1/2 2C plus 2 minus H. I'm not going to include the nitrogens and whatnot because we obviously don't have any. We only have carbons and hydrogens. So if we look at this, we've got 1/2. How many carbons? 2 times 6 is going to be 12. Plus 2 is 14. Minus 6 is 12. That gives us an HDI of 6. Or sorry, 4. Good. This is why I teach chemistry. So we've got an HDI of 4. What does that tell us?
There's 4 hydrogen Oh, yeah.
There's either 4 pi bonds, or there's 3 pi bonds, 1 ring, or there's 2 pi bonds and 2 rings, or there's 1 pi bond and 3 rings, or there's just 4 rings. But we've got some clues already, right?
It's aromatic.
All right, what was that again?
Aromatic.
It's aromatic. If we look at the proton signal, it's showing up smack in the middle of an aromatic region, right? So if we think about the aromatic ring we're most familiar with, what is that called? Benzene. So let's draw in benzene and see if we're right. What's the molecular formula for benzene? C6H6, right? And it's got 3 doubles and 1 ring, so it fits with our HDI. If we draw in all of our protons, are these all equivalent? Yeah, it's got rotational symmetry. They're all in the exact same environment. So if we were to label these would all be HA. And what sort of splitting pattern would they have? They have no 3-bond neighbors because we said that equivalent protons can't split each other. So this has 0 3-bond neighbors, which means that it will split as a singlet, right? So if we look at this, this is a singlet for HA. Does that make sense? This requires a lot of brain power. It's like a puzzle on steroids, and these will get progressively more difficult. So let's do one last one together. We've got C3H8O. So let's do the HDI again. We've got 1/2 times 2 times 3, which is 6 carbons, plus 2 minus 8, which means we've got an HDI of 0. So we've got a good clue that there's no rings in this, and there's no pi bonds in it, right? All right, so now let's start analyzing the NMR. It looks like we've got what sort of peak around 4? It's a little hard to tell sometimes with these guys, but the key is if you look at that center peak, it's got to either be a pentet, meaning split into 5, or split into 7, right? Because it's unsymmetric. So we know it's either going to be a pentet or a sextet. So we've got to kind of piece together this. If it's a sextet, let's just assume it's a sextet, how many 3-bond neighbors should there be?
Sextet?
So sextet is 7.
No, that's 6.
What's septet?
Oh, septet.
All right.
So it's 6.
So it has 6 3-bond neighbors potentially. All right. So let's kind of use our detective caps here and say this probably has 6 3-bond neighbors. What about this one around 2? Is that a singlet, doublet, triplet?
That's a singlet.
Looks like a singlet to me. Okay. If it's a singlet, how many 3-bond neighbors does it have?
0.
0. Has no 3-bond neighbors. All right, what about the peak right around 1? What is it? Yes, I am recording this. It's a doublet, right? So if we look at this one, it's a doublet. How many 3-bond neighbors should it have? Yeah. So it has 1 3-bond neighbor. Okay. So we've used our detective work. We can even analyze the chemical shift a little bit, but we know that this is in the range where it's not going to be an alkene, it's not going to be aromatic, it's not going to be an aldehyde, obviously, and it's not going to be a carboxylic acid. So it's probably going to be some combination of an alkane, right? So now what we can do, and oftentimes this is what chemists actually do, is they draw out the potential isomers. And then they try to look at those isomers and they say, which of these isomers fits the data? Okay, so we could say, all right, C3H8O could be propanol. Or what else? Okay, or isopropanol, right? So these are the 2 isomers. Which one do you think fits the data? So let's draw in the protons for isopropanol. Okay, if we look at the protons on isopropanol, I'm going to even change this last one to blue. We've got this HA proton on that alcohol. What about this one over here? It's its own, right? It's attached to a carbon that's attached to an alcohol that's attached to 2 methyl groups, so it's unique. What about these other methyl groups? So these are all going to be the same, these HCs. Is the other methyl group the same or different? Same, exactly. All right, so now if we look at HC, how many 3-bond neighbors are there? There's 1 3-bond neighbor, which means it should be split into what? A doublet, exactly. So we can immediately say, well, maybe this one, this doublet over here, corresponds to HC. What about this singlet here? What do you think that corresponds to? A. So we can say maybe this is HA. And then what about this last sextet? That could be HB, right? It has 6 3-bond neighbors, which means it's going to be split into a peak that's 7, right? So in this case, this is probably going to be HB. And if we look at our chemical shift chart, we know that HB is right attached to a carbon that's attached to an electron withdrawing group, which means it's going to be probably 2 to 4, right?
What about above the COH?
The which ones, HCs or?
No, the very top box on carbon with an alcohol?
So that would be for HA. So HA, if we look at the carbon alcohol one, that's going to be anywhere from 1 to 6.
That's such a wide range.
Exactly. I'll talk about that in a second, but if we look at HB, we said that HB is attached to a carbon attached to an electron withdrawing group, so it should be about 2 to 4. If we look at HC, it's going to probably be in that 1 to 2 range, which is where it is. And then alcohols. Why do you think alcohols show up in such a wide range? H bonding, right?
Oh, yeah.
Hydrogen bonding screws with spectroscopy, right? Because it depends on how well it's hydrogen bonding with neighboring solvent molecules. So the reason it shows up in all these different areas is because it can have different hydrogen bonding neighbors, and it's a very unreliable peak. Anytime you have a peak that hydrogen bonds, it'll show up in a variety of different locations. It's not a good diagnostic tool. All right, so what I'm going to do is I'm going to let you guys work on the remainder of these problems in the set. I'll post the key online. It'll be in the course notebook. Also online, you'll be able to pull up a mass spec problem set, which I put up here, and then there's also an IR problem set. So if you just want practice working through these as like puzzle problems, you can go through those, and I'll post all the keys online. I also posted a second NMR problem set, so if you're flying through these and you're thinking these are really easy, can you throw me anything more challenging, you can work through problem set number 2, but it won't be representative of what will be on the quiz. Problem set number 2 is more challenging because I haven't given you any other spectral data. Normally, if I gave you something like this, I would give you a mass spec and an IR, kind of like you guys had on your lab handout. So try to work through these this weekend. I know a lot of you feel overwhelmed with how challenging this is, but the more you practice these, the more you kind of train your mind to pick up these clues really quickly. So I'll let you guys work on this, and then we'll go around the room. If you guys want to push tables together or work in groups, this is a really good activity to work with partners on. All right, one other thing I forgot to bring up that's also a very useful tool that the book uses is if you go to the Skill Builder review section, there's a section 16.3 where it says you can predict chemical shifts pretty accurately for some of these. So if you look at a regular methyl group where it's CH3, it's typically show up at a benchmark value of about 0.9. If you look at a methylene where it's CH2, these typically show up at a benchmark value of about 1.2. And then the methynes typically show up at a benchmark value of about 1.7. So we use these benchmark values, and then we can say, well, are there any polar groups nearby that might shift them more downfield? And so in this example, they say, all right, we're looking at a methylene group, which has a benchmark value of 1.2. And then this alcohol is going to shift at 2.5 ppm downfield. So we can very accurately predict that this should show up at 3.7. So how many of you guys finished problem 3? You guys get ethanol for that one?
Yeah.
Where did your quartet show up?
Like 3.75.
Yeah, 3.7, right? So this very accurately predicted where that methylene set of protons should show up for ethanol. Another really useful one is anticipating groups that are attached to esters. So if you look at an ester, you take that benchmark value, which is 1.2, and then add 3 to it. So it should show up at about 4.2. So if you are looking for esters, you can use this cheat sheet a little bit. And then if you're next to a regular ketone, instead of adding 3, you just add 1, because it's not as polar as being next to an oxygen on an ester. So you can use this as a guide too. It's the Skill Builder 16.3 for those of you looking it up. I'll give this to you guys, like I said, on the cheat sheet. But with the cheat sheet, I'm going to slowly wean you guys off of it. So there will be someday, at some point in time, probably later this term or early next term, where I'm like, no, you guys gotta get these down. All right.
How do we know if we've got it down?
I'll know. Just to reiterate a point too, this X value here can be any electronegative group. It doesn't have to be a halogen. Oftentimes X's in organic chemistry mean halogens, but that can be any sort of electronegative atom. So that's one clue you can use too, especially if you're seeing peaks right around 3 to 4. They're probably next to a really electronegative group. All right, let's continue on and see how we can work through problems 3 through 12 on the in-class activity. If we look at problem 3, it's immediately clear that we've got 3 different sets of protons. We've got 1 proton set here, 1 proton set here, and 1 proton set here. Specifically, the one right around 4 ppm is a quartet, the one around 2.5 is a singlet, and the one around 1 ppm is a triplet. Another really useful trick when working through these problems is doing the HDI, or hydrogen deficiency index. And if you look at this molecule, it has an HDI that is equal to 0. So this indicates that there are no pi bonds and no rings in this molecule. If we're looking at the region around 3.5 to 4 ppm, we can see that there's a quartet. And if we go to our guidelines for trying to anticipate chemical shifts, we know that it should be close to an electronegative group. So let's go through it and try a few different isomers and see if we can see what we think might be going on. So one of the isomers could be dimethyl ether. The other isomer could be ethanol. So let's go through and see if one of these makes sense. Hopefully by now you can see that dimethyl ether is very symmetric. We should only have one signal for it, so we're probably not going to have this one. But let's take a look at the other one, the ethanol. If we look at ethanol, it's got protons on that terminal methyl group that are its own unique set, and it's got protons on the methylene that are its own unique set. So if we look at these methylene protons, they have 3 3-bond neighbors, which means that this will be split into a quartet. And then these methyl protons have 2 3-bond neighbors, which means that they'll be split into a triplet. So what I'll do is I'll go through and I'll label these HA, and then I'll label these HB. Then I'll label this last one HC. So if we go back to our chart, we can see that we've got a quartet that corresponds to HB. It's next to an electron withdrawing oxygen, so it's a little bit more downfield. If we look at the singlet, that falls in the range for alcohols. They show up a little bit irregularly. They can be anywhere from about 1 to 5 ppm. So this is going to be HC. And then our triplet over there is going to be our HA proton. All right, so it looks like all of our data lines up. That means that this compound is most likely ethanol. All right, let's continue on and work on problem 4. If we look at problem 4, if we do the HDI for this problem, it's going to be equal to 1. That means we have either 1 pi bond or 1 ring, and then we've got a quartet, a triplet, and a singlet in here. In particular, if we look at this quartet, it's right around 4 ppm, which is very high for most protons. It means that it's either attached to a very electronegative group or potentially some sort of alkene, although if we have an alkene, it'd be much harder for it to form a quartet. So let's go through and try to figure out what this molecule is. One option would be to have some sort of carboxylic acid group in there. But if we had a carboxylic acid group, we would expect a peak from about 10 to 12 ppm. So we know it's probably not going to be some sort of carboxylic acid. Another option is that maybe we've got some sort of carbonyl group plus some sort of alcohol in there. In this case, that could be the case, although we don't really see a broad singlet, which is indicative of an alcohol. We do have a singlet over here. So let's try to work through this a little bit, but keep in mind that normally when we see alcohols, they tend to broaden out a little bit. They're not these really big, sharp peaks here. This really big peak here tends to be something that contains more protons than just one. The other option that I think would work well for this is some sort of ester. So if we look at esters, and we go back to our correlation guideline, let me pull that up. Just one second. All right, sorry about that. So if we go and we look at an ester, we can see on this skill builder exercise 16.3 that the methylene carbons next to an ester should show up around 4.2, which in this case matches really closely with our observed chemical shift of about 4, a little bit above. So at this point, a lot of evidence is indicating that the compound that we're looking at in this NMR spectra is some sort of ester. All right, so now let's break this down a little bit further. And I'm going to put down 2 esters for this compound. I've got one ester here that corresponds to that same molecular formula. Or I've got another ester over here. So I've got the methyl group on the right coming off of the oxygen rather than the left coming off of the carbonyl. So if we look at this, I'm going to go through and label these protons. So I'll call this HA. And I'll call this one HB. And I'll call this one HC. If we look at the protons for HC, they have no 3-bond neighbors, which could correspond to the singlet right around 2 ppm. And another good way of checking is these are protons attached to a carbon directly next to a ketone. So if we go back and we pull up our table, we can say, all right, where do they show up typically if we're next to a ketone? All right, we've got a methyl group on there, which has a benchmark value of about 0.9. And then it's right next to a carbonyl group, so we're going to add 1. So 0.9 plus 1 means that it's going to show up around 1.9. So let's go back and take a look at where it's showing up. In this case, it's showing up right at 2. Perfect. So that's good indication that that methyl group could be next to a carbonyl group. Now let's take a look at HB over here. If we look at HB, it has 3 3-bond neighbors, which means it should be a quartet. And if we go back to our guide here, we can say, all right, if that's a methylene carbon, it means it has a benchmark value of 1.2. We take this 1.2 value and we add 3 to it. So if we do 1.2 plus 3, we get this value of 4.2 over here. So that quartet should show up somewhere around 4.2. Oop. And exactly, it's right over here. So we know that this is probably going to be HB. This singlet over here could be HC, and this one would be HA. Now, just for argument's sake, let's take a look at the molecule I have drawn right below. If we look at the molecule I have drawn right below, let's take a look at this methyl group. If we go back to our chart and we say, okay, this has 0 3-bond neighbors. If we did have this, it would be a singlet. And when we go to our correlation table, we can say, all right, if it's a singlet, it's a methylene peak right here. And it's right next to an ester. So we'd say 0.9 plus 3 wouldn't be 4.2, it would be 3.9 ppm. And if we go back to our in-class activity, we can see that our singlet isn't over in this region, it's actually over near 2. So we have evidence showing that it's not going to be this one. In fact, it's going to be the one on the top here. So let's erase this just so we're not confusing people. And let's go on to the next one. The next one, if we do the HDI for it, has a HDI of 1, meaning that it has 1 ring or 1 pi bond. And the tricky thing with this is we only have 1 signal here. So the question is, do we have a pi bond or do we have a ring? In this case, we've got 1 signal, which means that it has high elements of symmetry in there. And typically when I see very high elements of symmetry, I tend to think of things that are rings. So in this case, we could try to do a variety of different rings, but let's take a look at this particular ring. Oh. This is called 1,4-dioxane. And if we look at this, we have protons here and over here and over here. And the question is, are these all in the same or different chemical environments? Well, if you look at them, let's take this proton for example. The proton right next to it, coming off of the same carbon, is just in a different plane, but it's in the same chemical environment. So these are going to be the same. And then we also have a plane of symmetry going down the center of the molecule, which means the protons right below it are also in that same environment, meaning that they're right next to that oxygen too. They're just on the other side. So all of these are going to be HAs. And we know that protons that are equivalent can't split each other. So if we look at HAs, they have 0 3-bond neighbors, which means that it's going to split as a singlet, or in this case, not split at all. Alright, so that one was a little tricky. Sometimes you have to go through a process of guess and checking. I know a lot of you were trying to do 4-membered rings with alcohols coming off, but if you do any of those, you would be getting more than one peak occurring in the NMR, and in this case, we only have one. Alright, now let's do the next one. We've got another C4H8O. And if we do the HDI for this one, it's also going to be 1. So HDI equals 1. It has one ring or one pi bond. And one thing I'm noticing here is we've got peaks that are pretty upfield from a normal alkane peak. So there's got to be some sort of electron withdrawing group here. And again, this singlet peak here is pretty big. It's not very broad. It's probably not going to be an alcohol. So what I would do is, if it's not an alcohol, it could be some sort of ether. It could be some sort of ketone. We have to take a look at a lot of these. One thing it's not going to be is an aldehyde. An aldehyde would have a peak between 9 and 10 ppm. So in this case, it's probably going to be some sort of ether, or it could also be some sort of ketone. So let's take a look at some potential isomers and try to rule them out. Let's say we have, I don't know, some crazy looking ether. That would be C2. What if we have an ether like that? Well, if we had an ether like this, how many signals would we expect? Well, in fact, we would have a signal for HA. We would have another one for HB. Whoa. HB. And then another one for HC. And then HD. HD. And then this methyl group over here will be HE. So we could try to make an ether here, but we would have 1, 2, 3, 4, 5 peaks. We're really only observing 3 signals. So we know that immediately we've kind of hit a dead end here. But we can try to do some sort of ketone. So let's try a ketone. So if it's a ketone and we start out like this, we only have 3 carbons. So let's add on another carbon on one end. And let's draw in our hydrogens. So we've got a methyl group over here. We've got a methylene, which is that CH2 peak over here. And we've got a methyl group here. If we look at the methyl group on the left, these are all the same because we know methyl groups can spin like helicopter blades. If we look at the methylene carbons, or protons, they'll be equivalent. And then the last methyl group will be equivalent. So this does have 3 signals, which is perfect. So let's take a look at these HA protons over here. How many 3-bond neighbors do they have? Well, they don't have any, so it should be a singlet. In this case, we could maybe say, well, maybe this HA is our singlet. If we go back to our NMR guide, we can say, all right, we've got a methyl group that has a benchmark value of 0.9 ppm over here. It's right next to a carbonyl group. Let me erase all this stuff. So if we take 0.9 plus 1.0, it should show up around 1.9 ppm. So let's go back and check for in-class activity. Singlet's right above 2, so we're right on track. Now let's take a look at HB. HB has three 3-bond neighbors, which means maybe this quartet belongs to it, and maybe the remaining ones, HC, belong to this last methyl group over on the end. But let's just double check. We said HB shifted around 2.5. We can go check with our sheet, and we can say, well, methylenes have a benchmark value of 1.2. If we go over here, 1.2 plus 1 equals 2.2. So it should have a chemical shift around 2.2 ppm. And it's right around 2.5, which is pretty darn close to where it should be. So this looks like great evidence for supporting this ketone that we have drawn here. All right, let's go to a more challenging one. All right, so if we do the HDI for this one, it gets a little bit crazy. I'll let you guys do the math, but what it should be is 5. So this has a lot of either rings or pi bonds or a combination of both. One thing that stands out immediately to me is we've got 2 peaks in the aromatic region. The only aromatic system we've seen so far in class is a benzene. So we immediately have a clue that there's some sort of benzene in there. And then we've got another peak at above 12 even. That's very indicative of some sort of carboxylic acid group. So while we do have a HDI of 5, we've already accounted for 3 pi bonds in the benzene ring plus a ring, so that's 4. And then the carbonyl group in the carboxylic acid would be 5. So this works out really well. Okay, another thing to notice is we only have 2 peaks for our aromatic ring. If we only have 2 peaks, that means it's probably going to be symmetric, right? If we had groups coming off these positions, we wouldn't have 2 peaks, especially if we had R1 different from R2. If R1 was the same as R2, we could have 2 peaks. But typically we observe this sort of splitting when we've got R1 and R2 like that. It's a very common pattern. These are actually both doublets if you zoom on them quite a bit. So maybe this carboxylic acid is coming off of one of those positions. And then we've got to ask ourselves, all right, what are we missing? It looks like we're missing a carbon and an oxygen. So let's try to include those in. And the question is, would it be a carbon and then an OH? Or would it be this carboxylic acid where, ooh, that's a bad drawing, where one of these is a carboxylic acid and then the other end is some sort of ester? We've got to decide here. And what it comes down to a little bit is looking at the shift. If we look at this one on the left, we would have protons here and here, and then we'd have another set here, and then we would have a set here. So we'd have 1, 2, 3, 4, 5 signals in this NMR. This one we only have 4. So we know immediately it's probably not going to be that alcohol. We don't have enough signals to correspond to that. So let's take a look at this one over here. And in particular, let's try to label all of our protons. So I'm going to go through and label them as blue. So I'll label this HA. If we look down here, these are both HBs. These will be both HCs. And then I'll label these HDs. And let's see if we can assign these. So let's start with HA. We said that that's probably a carboxylic acid proton, so I'll label these HA. Then if we look at HB, it has 1 3-bond neighbor, so it should be a doublet. It's going to be one of these. I'm just going to arbitrarily assign it as that. We'll, if we have time, we'll cover how to predict where these are. And then this other one will be HC. We know that both of them are in the aromatic range. We don't know their relative position very easily. HD has 0 3-bond neighbors, so it's going to be probably this large singlet here. You can tell it has more protons since the area underneath it is much, much larger than, let's say, the signal for HA. So this integration area, the area under the peak for HD, is going to be 3 times the area under the peak for HA. All right, let's continue on. We've got C3H6O. This has an HDI of 1, meaning it has one ring or one pi bond. In this case, we could try doing both. Let's take a look at different ring systems. So if we have C3, we could have this as one isomer, right? Or we could have this as one isomer. Those are our possible ring systems. If we have a pi bond, we could have a few different options. We could have this. Oh, I'm missing one. So that's C3H6O. We could have something like this, or we could have one where there's a double bond between a carbon and an oxygen, kind of like that. Another one we could have, just to be very thorough, would be to have some sort of aldehyde. So let's go through and look at these isomers and try to rule some out. So if we look at the ring one over here and try to predict how many signals it has, we can say, well, there's got to be proton signals for these guys, right? That would be HA. Then we would have HB. And then this alcohol would be HC. There should be 3 signals for that, so it can't be this one. Let's do the next one. We should have HA, HA, and then HB, HB. So 2 signals. We only have 1, so we can rule that one out and say, well, it can't be that. The next one should have 3 signals, one for these methyl protons, one for the methylene protons, and then one for the aldehyde. We also don't have an aldehyde peak in the 9 to 10 range, so we know it can't be an aldehyde. It's not going to be this one. If we look at the next one, it will also have too many signals. We'll have one for this methyl group. It'll have one for this proton, one for that proton, and one for this alcohol. So we'd have 1, 2, 3, 4 signals. We only have 1, so it can't be that. Hopefully you're kind of seeing the pattern here. This one we would have a signal for this guy, signal for that guy, signal for that guy, signal for these protons, and then this alcohol. It's way too many protons. Last but not least, we can say, well, what about this compound? What about acetone? Are the protons on the left the same as the right? Yeah, because there's an internal plane of symmetry going down this molecule. All of these can be considered HA protons. So right now, immediately, we can say this is probably going to be acetone, not any of the other isomers we had drawn. So sometimes guessing and checking, especially with simple molecules, works very well. All right, let's do the next one. If we do the HDI calculation for C9H12, we get a HDI that equals 4. Another big thing we've noticed is we've got peaks in the aromatic region. This screams benzene ring, right? So we know it's probably a benzene ring with something coming off of it. In this case, the benzene peaks all in this aromatic region look like they're pretty clumped together. Usually when you see this splitting pattern, it means that either you've only got one substituent or you don't have very good symmetry. So in this case, we're missing 3 carbons coming off of it. So let's say we're maybe missing this guy. We could ask ourselves how many peaks that are non-aromatic, meaning they're not coming off of the benzene ring, should there be? Well, we'd have 2 protons here in a set. We'd have 2 protons here in a set. And we'd have 3 protons coming off the end. So it's probably not going to be that. We only have 2 other peaks that are non-aromatic, so it's going to be some other different configuration. Let's try this one, where we have an isopropyl group coming off. If we do this, we've got protons here. I'll call these HA. We've got protons here, and the question is, are these 2 methyl protons or methyl group protons the same? Yeah, they are, because we said an isopropyl group can spin around like a helicopter blade. There's an equal probability of them being in the same space. One thing people forget is that we have an additional proton here. So we'll call this HB. And then let's go through and label these. I'll label this HC and HD and HE. If we look at this proton down here, it's the same as HC. This one's the same as HD. So now let's analyze this, starting with HAs. So if we look at these HA sets, over here and over here, they have one 3-bond neighbor. So we've got 6 protons with one 3-bond neighbor. That means it's going to be split as a doublet. So maybe this doublet down here is HA. Okay, that works. What about HB over here? HB has 6 3-bond neighbors, which means it's going to be split into a sextet. So maybe it's this guy over here. Additionally, we know that HB is on a carbon that's attached to an aromatic ring. So let's go back to the chart. Pull that up. One good trick to use is that these peaks that are carbons attached to aromatic rings typically show up around 2 to 3. So let's go back to our in-class activity. Yeah, it's right around 2 to 3, so that fits pretty well. And then we have to ask ourselves, well, what's going on in the aromatic region? So how many partners does 3-bond neighbors does HC have? 1. So HC should be a doublet. What about HD? HD gets a little trickier because it's being split by 2 different types of neighboring protons. It's being split by HC, which is a 3-bond neighbor, and it's being split by HE. So in this case, HD would be one of these weird examples of a doublet of doublets. Some people will say, well, it's got 3-bond neighbors, so it's triplet-like. I'd be fine with either of these. Oftentimes you can make out those doublet of doublets, other times you can't very easily. And then if we take a look at HE, it's got 2 3-bond neighbors, and these HDs, one 3-bond neighbor. And in this case, they're equivalent HDs, right? So if we think about this one, let me rephrase this and step back. These HDs, there are 2 of them in that position, so we can say that this one should be split as a triplet. So if we look at this one, it's a little confusing here, but what this is it's overlapping. It's an overlapping mess of signals that are HE, that triplet, HD, which is our doublet of doublets or our triplet-like doublet of doublets, and then our HC signal. So those are all overlapping there. This one I thought was pretty challenging. The key being is when you only have one substituent coming off of an aromatic ring, those remaining signals tend to clump together and overlap really well. Whereas if you look at our other example up here, when you've got substituents coming off of other positions, meaning not just one substituent coming off the ring, you tend to get much nicer looking splitting patterns. All right, let's do problem 10. Problem 10, if you do the HDI for this one should be 1. We only have one signal. That means it's highly symmetric. That makes me tend to think of rings. So if we think about this, we could do a ring that is 6 members. And if we did this, we'd have 12 protons. And the thing a lot of people have asked about is they said, well, cyclohexanes are in chair conformations, right? So if we draw our chair conformation like this, we know that we've got axial protons and equatorial protons, and those are not equivalent. At least if we freeze this in time, The axial protons are in a different space than the equatorial protons. The problem is the NMR doesn't take an instantaneous snapshot. It actually looks over a period of time, and this chair conformation can actually flip. So now if we look at these protons, one of them, actually let me do it this way, and I'll label these H axial is now in the equatorial position, and HB, which was equatorial, is now in the axial position. Cyclohexanes will flip-flop and do this inversion of a chair or chair flip, and so over time they tend to average out and share the exact same signal. So if we look at cyclohexane and we look at it in the NMR, it's not locked into one conformation. It's actually rapidly flipping at room temperature, and so all of these protons are going to be equivalent because they're all going to average out over time. If we appended a tert-butyl group onto cyclohexane, then we could lock that tert-butyl group into the equatorial position, and we could actually resolve equatorial versus axial protons. But in this case, we're more concerned with the chair conformation. Let me actually leave this up here. I was going to erase it, but... and I'll just label this as fast inversion. So all of these are going to be HA. There are no HB protons because that HA and HB signal will average out. Alright, number 11 was pretty tricky, I thought. The last two I thought were more challenging than the others. This one has an HDI of 1. Meaning there's some sort of double bond in it. Again, you can see the signal around 4, which anytime I see a quartet around 4, I tend to think of an ester. So let's just start by creating this skeleton that includes an ester, and then we have to figure out what's coming off this end on the right and this end on the left, and try to identify what substituents are coming off there. The other thing some people had trouble seeing was this little hump between 4 and 5. This strongly indicates that there's some sort of hydrogen bonding group going on there. Something that really likes to hydrogen bond, tends to broaden out really well. Peaks that do this are occasionally alcohols, or things like amides, phenols, things like that. In this case, it's showing up around 4 to 5. That's where alcohols, amines, and amides show up. Phenols don't typically show up in that region. So let me move this over. And this is one you may want to try guessing and checking on quite a bit. But one thing I have noticed is that this peak at 4 probably corresponds to protons coming off of here, just like we've already seen. And then there's a triplet over here, which is probably these terminal methyl groups. So oftentimes when I look at NMRs, I look for triplets and quartets. Triplets and quartets oftentimes are a good hint that there's some sort of ethyl group there. So I'll label these HA, and then HB. We know that this is HA, this one's HB. And then we've got these remaining 2 peaks over here and over here with this hump. If we look at our molecular formula, we're missing a nitrogen and we're missing a methyl group. So one functional group we haven't seen is this one. This functional group is called a carbamate. It's very commonly found in plastics like urethanes. It's a common functional group that we haven't really discussed yet. So if we look at this methyl group coming off the end, we could call this HC. HC has 0 3-bond neighbors because we can't go through that nitrogen. So if we look at that, this could be HC. And then if we look at this amide down here, this HD, that's going to hydrogen bond really well because it's an amide group over here. And amides are very electron withdrawing, means that this will be an excellent H-bond donor. All right, so we can label this one as HD. So this one's pretty hard. Like I said, it's a new functional group called a carbamate. And this was meant to be one of the more challenging problems on the problem set today. All right, the last one, if we look at it, it's got a HDI of 0. And in this case, we've got a peak really far upfield, actually in the region where we normally see aromatic protons, but we know that it can't be aromatic because we've got an HDI of 0. So in this case, we know it's going to probably be very symmetric, but it can't be a ring. So it's got to be some sort of linear molecule with a high degree of symmetry. So we've only got 3 carbons. That's our backbone. It's symmetric. Whatever is coming off of it needs to be the same on the right as on the left. And then we've got 6 chlorines coming off here. So let's take a look at a couple options. We could have 3 chlorines coming off of each end. And then we could have protons here. That would only be one signal, right? Because each of those protons is in one environment. Or we can say, well, what if there are some protons coming off the end, and then you've got 2 chlorines here, 2 chlorines here, and then chlorines here and here. We've got a decision to make. If we're looking at the protons of interest, they're going to be equivalent on the right and the left. But we've got to ask ourselves, which proton is more likely to be shifted all the way over into the aromatic-like region? And so we've got to ask ourselves, which one's bonded to the most polarized carbon? And in this one, you can see it's bonded to a carbon attached to 2 chlorines. In this one, it's attached to 2 trichloromethyl groups. And in this case, this one is actually more polarized than the one on the top, which means that this one is probably the better candidate for the NMR that we have drawn there. Although this is a pretty hard problem, and I'll say it won't be this one will be HA. So it's a pretty tricky problem. Those of you that were able to get through this will definitely do well on the exams and quizzes. If you struggled with this, don't be discouraged. Try to work through the sapling problems as much as possible. Do the problems from the book. The more you do this, the more you can see these tricks, like immediately identifying aromatic protons, quickly doing the HDI calculation, and so on. The other activities that I posted on the website and in the course notebook, I'll post the key to later today. All right, good luck studying, and let me know if you have any questions.